Hello friends, so today we are going to solve 5 questions, and these 5 questions are from more or less related with our capacitor, and in general we can call this as electric fields around the conductor. So one second. Okay. So these are some basic questions about the capacitor. Not much of tough problems are these. So in the first question, we are given that a 100 picofarad capacitor is charged to 100 volts. After charging, battery is disconnected. The capacitor is connected in parallel with another capacitor. If the final voltage is 30 volts, what is the capacitance of the second capacitor? How much energy was lost? Because initially we are having only one capacitor. It is charged and then it is disconnected from battery and it is connected with the second capacitor, whose capacitance we are going to find out. And in this case, as the battery has been disconnected, therefore we can easily use the conservation of charge. Okay. So for that, let us start with our first capacitor. So we can say that initial charge on first capacitor on first capacitor, and let us call this as Qi. Then this Qi will be equal to C1 multiplied by V1, where C1 is the initial capacitance of our and V1 is the voltage across it. So we are having 100 picofarad and it is charged to 100 volts. Okay. So this gives us 10,000 picocoulombs. And okay, let me write it. This is our picocoulombs. And after this, you can see the disconnection from the battery, it is connected with another capacitor, and those capacitors are now in parallel. Therefore, we can say after total capacitance and so let us call this as CT, and the CT will be equal to now C1 plus C2. Okay, because after disconnection from the battery, another capacitor is connected and these two capacitors are now in parallel. So C1 is in parallel with our C2. And therefore, we can write that our final charge and let us call this as our QF will be equal to our total capacitance multiplied by the final voltage. Total capacitance is our C1 plus C2. So we can write this as C1 plus C2 times final voltage. And we have already removed the battery. Therefore, we can easily use the charge conservation. So we can say by charge conservation, our initial charge should be equal to our final charge. So our initial charge was our C1 V1 and the final was our C1 plus C2 times final voltage, and we are supposed to solve it for C2. Therefore from here we can write that our C2 will be equal to, we can take C1 as common, and this will be coming as our V1 upon Vf minus of 1. Now it is quite simple. So we get our C2 is equal to, C1 is given to us over 100 picofarad, and V1, that is initial voltage, or over 100, final voltage is over 30 minus 1, and this approximately will be equal to 233 picofarad. So this is the value of our final second capacitor, which was connected in place of battery. Okay. And the second part of this, we have to suppose to find out the energy lost. So for energy lost, we are first of all going to find out the initial energy. So initial energy is, let us suppose, over Ui, and that will be equal to over half C1 V1 square, and this comes as our half multiplied by 100 picofarad and multiplied by our 100 voltage and its square. Therefore we get that our initial energy will be approximately equal to 5 into 10 to the power minus 7 joules. And similarly we are going to find out the final energy. And the final energy is our UF, which is equal to our half, and there are now two capacitors and both are in parallel. So C1 plus C2 multiplied by final voltage square, and so this comes as our half C1 and C2. C1 is our 100 picofarad and C2 we just found is 233 picofarad, and multiply by voltage given to us as 30 whole square. Therefore we get that our final voltage, final energy will be approximately equal to 1.5 into 10 to the power minus 7 joules. So energy lost will be the difference between the two. So we can say our energy lost will be equal to, let us call this as delta U, is equal to our initial minus final. So we get this as 5 into 10 to the power minus 7 minus 1.5 into 10 to the power minus 7. So we get that energy lost delta of U is approximately equal to, this will be coming as 3.5 into 10 to the power minus 7 joules. Okay, so in this case we have to remember that when the capacitor is charged and the battery is removed, so charge is always going to remain conserved. How many times if the battery is removed, and if battery is connected, then the potential is going to remain constant. Okay, so we have to remember this particular thing. Next question. So we are given two coaxial aluminum tubes are 30 cm long. The outer diameter of the inner tube is 3 cm and the inner diameter of the outer tube is 4 cm. When these are connected to a 45 volt battery, how much energy is stored in the electric field between the tubes? So we have two concentric tubes basically, okay, and these will be behaving like a coaxial capacitor of length 30 cm. We are going to solve it for a length L, and later on we can substitute value of our, that's our length. So it is directly based on the formula itself. So we can say that coaxial capacitor of length L, inner radius is suppose A, inner radius is our A, and outer radius is suppose B. Therefore we can write that is capacitance C will be equal to, that is standard formula, 2 pi epsilon naught times L, and we have this as natural log of B upon A. And so all the things are given to us, so we simply substitute it. We get this as 2 pi epsilon naught is our 8.85 into 10 to the power minus 12. Length is given to us our 30 centimeters, so this will be 0.30, and natural log of, we are having our A is 1.5. okay, so their diameter is given, so this comes as 1.5 divided by 2, and this capacitance approximately will be coming as 58 picofarad. And we are also supposed to find out energy, and we have to remember that energy will be stored only in the electric field. Okay, that will come to later part also. So we can say stored energy that is our U will be equal to over half CV square. So this comes as our half. Capacitance we found out is of 58 picofarad, and voltage is our 45 volt. Therefore we get that this value of stored energy U is approximately equal to, this will be 58.7 nanojoules. Next question. It states that calculate the electrical force that acts on one plate of parallel plate capacitor. The potential difference between the plates is 10 volts and the plates are squares 20 centimeter on side with a separation of 3 centimeter. If the plates are insulated so the charge cannot change, how much external work could be done by letting the plates come together? Does this equal to the energy that was initially stored in the electric field? So this they have, you can say, twisted or manipulated the question in a little bit lengthy way, but it is quite simple that first of all we have to find out the electric force, and it is only asked for only one plate, and then we have to find out if we try to bring all the plates closer to each other such that the distance between them becomes approximately equal to 0, and then we have to find out what will be the work done required for that. Okay, and for that, for electric force, we are going to find out the electric force based on the energy stored in the electric field. Okay. And okay, so let's start from there. So we can say that now we are going to call this as initial and final. Initially when their position is fixed. Okay. So we are given square plates, and the square plates, the length is suppose of L, and that is given to us as a 20 centimeter, so that will be 0.2 meters. Okay. And obviously the area will be our length square, and that will be 0.04 meter square. And plate separation, that is our D, it is our 3 centimeter. So you can say this is 0.03 meters. Potential difference, that is our V, is given to us as 10 volt. So these are the things that is given to us. So first of all, let's find out what will be the capacitance, parallel plate capacitor. So we can say that our capacitance C is our standard formula epsilon naught A upon D, and epsilon naught is our 8.85, 4 into 10 to the power minus 12. Area we found out is 0.04, and the distance is 0.03. So this will be approximately equal to 11.81 picofarad. Okay. And now we are going to find out our electric field. Okay. And so we can say that our electric field is nothing but our the potential difference divided by the plate separation. So we can say that our electric field that is E will be equal to potential difference and the distance between the plates. So this will be 10 and 0.03. So this will be equal to our 3.33 volts per meter. Okay. And from here we can easily find out the charge density on the plates. So we can say our charge density, that is our sigma, will be equal to epsilon naught times our electric field. So this comes as 8.85 into 10 to the power minus 12 multiplied by, this is 333.3. So we get that our charge density will be approximately equal to 2.951 into 10 to the power minus 9 coulomb per meter square. And from here we can find out now total charge on one plate. Total charge on one plate, and that is our Q is equal to charge density multiplied by the area. Okay. And that will be equal to over 1.81 into 10 to the power minus 10 coulombs. Okay. And we are supposed to find out the force only on one plate. Okay. So the final is our force on one plate. Okay. Because we know that we are going to have two plates like this, and obviously one is going to have a positive charge, other one is going to have a negative charge. Okay. And this will be Q as well as our Q. Okay. So let's find out. We consider the positive plate. Okay. So it means basically we are going to find out that the force that will be because of the electric field acting on the charge. So let us consider the positive plate and find out the field due to negative plate alone. So the force on one plate, and this one plate we considered this as our positive charge. And so we are going to find out a field due to negative plate. Field due to the negative plate, and let us call this as our E negative, will be equal to our charge density divided by our epsilon naught. Okay. And obviously that is nothing but a value of our E. Okay. And it will be acting towards the negative plate. And so now we can easily find out our force. So force on the positive plate, let us that is a F, will be equal to the charge and the value of the electric field. And charge is our Q times A, electric field is our sorry, not Q times A, but charge density multiplied by A, and this comes as charge density by epsilon naught. Therefore we get that the value of force F is equal to our this sigma square times A upon epsilon naught. And this will be okay. Now we can substitute value of our sigma, and we know that our sigma is equal to where it went. Okay, let me write it. I think I missed it. So charge is equal to our epsilon naught V upon D. Okay, in terms of the potential and our distance between the plates. And therefore we get that the value of force will be equal to our epsilon naught A, and this comes as our square V square upon D square. Or we can also write this as our capacitance C V square by D. Okay, because our capacitance is nothing but epsilon naught A divided by D. Okay. And so we are supposed to find out the work done in bringing the plates together. Okay, and the charge is constant. So we can say external work to bring plates together, and they are having constant charge. And because it is given that they are insulated, so the charge is our Q, and this is going to remain constant, that is, it is our fixed value. Okay. And for the sake of convenience, because we have to do some here calculation, let us assume that the separation varies from x equal to D and to x is equal to 0. Okay. So we can say that let the separation varies from x is equal to D to x is equal to 0. And therefore we can say at any instant we can write the capacitance of the capacitor, that we are going to call it an instantaneous capacitance. Therefore we can say the instantaneous capacitance, that is with C, and this C is dependent upon our x, because x is changing from D to 0, and in between it can have infinite number of values. Therefore we can say that C of x is equal to, we can write this as our epsilon naught A divided by x. And from here we can find out, for this particular instant we can easily find out what will be the value of stored energy. So we can say the stored energy is our U of x, and we are going to write it in the form of the charge because charge is constant. Okay. So we can say this will be our Q square twice and our capacitance, and we can substitute value of capacitance, so that we get this as our Q square times X, and this is 2 epsilon naught times A. Therefore our force, so you can say force, let us suppose that is F, which will be also dependent upon the value of X, is equal to the negative of our derivative of our energy, and this gives us minus Q square upon 2 epsilon naught times A. And from here we can easily see that the value of the force, that is our F, is independent of X. So it means whatever the distance between the plates is, it is not dependent upon the separation. Okay, it is only dependent upon the charge and the area. Okay. And now we know the force, we can easily find out the work done. Therefore we can say our work done will be our force and times dx. Okay. And it is going to vary from a distance d finally when x is equal to 0. So we simply substitute value of our force, that is our d, to 0, and this comes as our Q square x, sorry, one second, oh sorry, there is no x, and 2 epsilon A times dx. And from here we get this as our Q square d 2 epsilon times A, and let us call this as energy at U at a distance d. And our okay, if we look closely, this is nothing but our, one second, where we found, I think we, okay, so we have not calculated it, so let me calculate it. Okay, so we can find out our initial energy, and initial energy is suppose our U of I, and that is equal to nothing but our at any position d. Okay, and this comes as our Q square d upon 2 epsilon times A, which is our 5.903 into 10 to the power minus 10 joules. And obviously at x equal to 0, when plates are touching each other, we can write that value of energy will be equal to 0. So which means that our work done is nothing but equal to our initial energy. That was our question answer. Okay. So it means the field energy is our equal to our initial work done is equal to our initial energy. Next question. Okay, it states that it has having two parts. So this is part A, sorry. So it was having two parts. So this is our part A. It states that the plates of a capacitor have area A, separation S, assumed to be small. The plates are isolated, so the charge on them remains constant. The charge densities are plus and minus sigma. A neutral conducting slab with same area A but thickness S by 2 is initially held outside the capacitor as in figure. The slab is released. What is the kinetic energy at the moment it is completely inside the capacitor? Okay. And part B, same question, but now let the plates be connected to a battery that maintains a constant potential difference. The charge density initially are plus and minus sigma. So basic figure is given to us. The distance between the plates is S, plus and minus, and there is slab which is moving inside the plate, and it is exactly at the half point. Thickness is half. Okay. And part A, it is isolated. Part B is it is connected with the battery. Okay, so we have to remember that. So we have our part A, and part A is having our isolated. So it means the charge densities will be remaining as plus and minus sigma. And the slab, let us suppose its thickness is over T, and where T is equal to over S by 2. And it is drawn into the capacitor. So as it is being drawn into the capacitor, it is going to acquire induced charge. Okay. And we have to find out that what is its kinetic energy when it is completely inside the plate. Okay. So we are going to find out we are going to use the initial state when the slab is completely outside. So inside here it is only filled with our air, and when the slab is completely inside, it is consisting of our air as well as our slab. Okay, so that we have to remember. So we can say our initial state and this initial state we are having slab outside. So it means this parallel plate capacitor is having only the air, and then we can write the charge is, let us suppose, our Q, and that will be charge density multiplied by the area. And from here we can easily find out our energy. So we can say our initial energy this initial energy is our suppose U of I, and that will be equal to Q square upon 2C. Q square upon 2C. Q we already know, so we can write this as our charge density multiplied by area whole square, and capacitance of a parallel plate capacitor we know is our epsilon naught A and divided by the separation, that is our S. Therefore we get that our initial energy is equal to, and this will be our charge density square multiplied by A and multiplied by S divided by 2 epsilon naught. So this is the initial energy in the parallel plate capacitor when the slab is completely outside. Okay. And when, so let me draw the figure. So these are the plates of the capacitor. Now the slab is completely inside. Okay, so this is a slab. So initially the thickness, the distance between the plates is given as S, and the thickness of the slab is our S by 2. So therefore this distance will be also our S by 2. So now we are having two capacitors. Okay. And so let us assume this is our capacitance C1 and this is having capacitance of C2. Okay. And okay, and in this case it is the sheet or the slab is given to us as a neutral conducting slab. Yeah, it is given as neutral conducting slab. Okay, and area is same. Area is the slab is same. So it means these two capacitors C1 and C2 will be effectively now in series. Okay, and the areas A and their thickness respectively will be equal to S by 2. Therefore, we can say that our final state is slab is inside. Slab is inside. Therefore, from here we can write that the effective geometry this gives us two capacitors which we have said that there will be C1 and C2 and they both are in series. And both are in series. Their thickness is our S by 2 and A is our area. So you can write that our C1 will be obviously equal to C2 because all the parameters are same. And this comes epsilon naught A and the distance is our S by 2. So this gives us 2 epsilon naught A divided by S. Now we can find out the equivalent capacitance. So we can say the equivalent capacitance will be equal to, both are in series, so that will be 1 upon C1 plus 1 upon C2. And one second. And therefore this will be equal to our C1 C2 divided by C1 plus C2. Okay. And so we can say that our C equivalent, or let us call this as C final, okay, because much more easier initial and final. So C final will be equal to us as our, let me write it in the standard format so we can easily calculate, 1 upon C final 1 upon C1 plus 1 upon C2. So this comes as our S by 2 and this will be our epsilon naught A plus S by 2 and we have epsilon naught A. So you can clearly see this will be equal to S upon epsilon naught A. Therefore, we can say our final capacitance will be equal to epsilon naught A upon our S, and that is nothing but our initial capacitance. Okay. And now, okay, so in this case, we have to remember that energy is stored because we have a conductor, and that conductor is let's find out what will be the energy stored. And so we can say the energy stored only where the value of electric field is not equal to 0. Okay? So which basically means we are only interested in the air gap volume. Air gap volume. Therefore we can say that our final energy will be equal to over half epsilon naught E square multiplied by the volume, which is our air gap. And we can easily sort it out. So this will be epsilon naught, and electric field is, we know, our charge density divided by epsilon naught whole square, and volume will be our area and its thickness of our air, that is S by 2. Therefore we get that our final energy will be equal to our charge density square A times S, and this comes as our 4 upon epsilon naught. Now we can easily find out, because the loss of energy will be nothing but our gain in the kinetic energy. So we can say that our kinetic energy will be equal to the difference in the energies, and this is a sigma As upon 2 epsilon naught minus sigma square As upon 4 epsilon naught, and this comes as our sigma square A times S, and this will be 4 epsilon naught. So now we come to part B. And part B, battery is connected, so we are going to have a constant potential. Constant potential. Because battery is still connected. And therefore we can say that its initial energy that is our Ui will be equal to our half and Ci V square, and that will be nothing but our charge density A multiplied by S and twice epsilon naught. And then we already know when there is a slab inserted, okay, and everything will be same with respect to part A. Only thing is that our potential is fixed by the battery. Okay, we have to remember that. So we can say our final, and final is our slab is inside, but here battery is connected. Okay. Therefore we can say that our V is fixed. It is not going to change. Okay. V is fixed by battery. Potential is same. So geometry is also going to remain same. Therefore we can say the equivalent capacitance will be also equal to same. Okay. Therefore we can say same geometry. So if the geometry is same, therefore we can say that our final capacitance is equal to our initial capacitance, which we found in our part A, and that is equal to our epsilon naught A upon S. Okay. And the final energy is our U final, which is equal to half C final V square, and that is nothing but our U initial. Okay. There is no change in our energy U. And now, because battery has to do work, because it wants as it is connected, so the potential is to be remain same. Okay. So in this case, this is at the parallel plate, and now we are having a slab which is inside the plates, and the battery is still connected. Okay. If battery is connected, so it means the potential between these 2 points will be same. It should not change. and in order to maintain the same potential, this battery has to do some work. Okay, so we are going to find out the work done by the battery. Okay. So we can say the battery work and the battery works because maintain charge at constant V. Constant V. Therefore, we can write that the work done by the battery will be equal to potential and the charge difference. Okay. So we can write this as our V, and this is our Q final minus Q initial, which will be equal to 0. And therefore the kinetic energy is equal to our battery minus, and we have our final energy minus initial energy, where it is nothing but our equal to 0. So it means as the slab enters, quasi-statically the battery adjusts the charge to keep voltage as constant. So there is no net energy transfer to the motion. Because basically, as per the conservation, if something is lost, obviously something has to be gained. Okay. So but in this case, the battery adjusts the charge to keep the voltage constant. So there will be no net energy transfer to the motion. Next question. It states that a cylinder of 4 cm outer diameter hangs with its axis vertically from one arm of a beam balance. The lower portion of the hanging cylinder is surrounded by a stationary cylinder coaxial with the inner diameter 6 cm. Calculate the magnitude of the force tending to pull the hanging cylinder further down when the potential difference between the two cylinders is held at a constant of 5 kV. So we have two cylinders. So we can just draw an approximate figure. And so we are having two cylinders. Suppose this is our inner cylinder. And coaxially it is partially lower portion is surrounded by a stationary cylinder. Okay, so this is our inner cylinder and it can move in the downward direction. And coaxially it is surrounded by a outer cylinder like this. Okay. It is not given how much they are overlapping with each other. Something like this. And our this inner is having a diameter of 4 cm. So this is our suppose 2 cm, and this is our 3 cm. And it is hanging. Hanging doesn't affect anything. Okay, it is just hanging through the beam. It's connected somewhere so that there is no free fall of the cylinder. That's the only purpose of hanging. So we start with our given things, that we are given that the inner cylinder, which is a hanging, inner cylinder which is our hanging, its radius, let us suppose that of A, it is given as 2 centimeters, so that is 0.02 meters, and we are having the outer cylinder which is our fixed, and its diameter is given to us as 6 centimeter. So that will diameter is 6, so radius will be 3, so this will be 0.03 meters. So basically this is going to act like a you can say coaxial cylindrical capacitors. Only thing is that as it is going to move, inner one is going to move inside in the downward direction, the value of the overlap or the length of overlap is going to change, so capacitance is also going to change. Okay. And we already know the formula for our coaxial capacitor. Okay. So we can say the capacitance of a coaxial capacitor that is C will be equal to over 2 pi epsilon naught times L, and this is natural log of B upon A, and this L is nothing but a length of our overlap. So this is our L. Obviously it is going to change as it is going to move downward. Okay. So here we are going to find out, because length is not given, so we are going to do it our capacitance per unit length. So you can say capacitance per unit length, and let us call this a small c, which is equal to capital C upon L, and this is equal to over 2 pi epsilon naught and natural log of B upon A. And in general, let us suppose that our overlap is our x, okay, because we have to solve it for a variable. Okay. So let us assume that for overlap length x, so we can say its capacitance C, which will be dependent upon x now, will be equal to 2 pi epsilon naught natural log of B upon A times x. And now let us find out what will be the our, because we need to find out the force. Yeah. Okay. And this force, we are going to solve the value of, find the value of the force based on our energy consideration. Therefore, we can say that energy stored in the capacitor is, suppose, our U, which is equal to over half CV square. And because our this inner cylinder, suppose, moves by a distance of our dx, okay. So therefore the overlap is going to increase by dx, which is going to increase our C, okay. And because it is still connected to the battery, so we have to make some calculation with respect to the work done by the battery also. Therefore, we can say that our inner cylinder moves by our dx, and therefore our capacitance was C, so this capacitance changes by dc. And let's find out the energy stored in the capacitor change in energy stored when it is moved by a distance dx. So we you can say our change in energy, that is our du, will be equal to our half V square and change in our capacitance. And similarly, we can find out the charge on the capacitor change. So we can say change in the capacitor charge. Change in the capacitor charge. And that is our dq, and that potential is same multiplied by the change in capacitance, that is our dc. Now in order to maintain the same potential, because the battery is connected, the battery has to do some work. Therefore, you can write that the work done by the battery is suppose of a dw, and this for battery will be equal to the change in the charge multiplied by the potential. And dq we know our vdc, so this comes as our v square and change in the capacitance. And now we can easily use the conservation of energy. So it means that the work done by the battery will be equal to the increase in the stored energy plus the mechanical work done. So you can say energy conservation and by energy conservation, the work done by the battery will be equal to the change in the energy plus the, you can say, mechanical work done, that the force multiplied by the distance moved. Distance moved is our dx. You can say this is equal to v square multiplied by the change in capacitance, half v square dc plus f multiplied by dx. So from here we can say that the force and dx will be equal to over half v square times change in the capacitance. And therefore from here we can say that the value of force is equal to over half v square dc by dx. And value of capacitance we already know for a cylindrical capacitance. And this V is our equation number 1. So we can say from equation 1, we can write its derivative will be equal to 2 pi epsilon naught times natural log of B upon A. Therefore, we substitute back into the force equation. So we get our force is equal to over half V square, and this comes as our 2 pi epsilon naught natural log of B upon A. And this 2 and 2 cancels out. So now next is simple calculations. So we are left with this is a pi epsilon naught, and this is a pi epsilon naught is 8.854 into 10 to the power minus 12, and voltage is given as 5000 horse square divided by natural log of B is our 0.03, A is 0.02. So we get the value of the force is approximately equal to 1.715 into 10 to the power minus 3 newtons. So this is the value of our force. So these were the 5 questions which were related with our different types of capacitance. First two was comparatively easy, and this one, last one, was a little bit tricky in terms of the formation of the question. Otherwise it is quite easy to solve. And we have to remember, especially in the case of the capacitors, then when we are having a capacitor which is connected to the battery, and if the battery is removed, we can directly use the charge conservation. Okay. And if the battery is still connected, then we come back to the potential difference is to be remaining as a constant. Okay. So these are the two basic variations, especially with respect to a capacitor. Okay. Like in the first part, in the first question, we were having a capacitor and that was connected to some battery, and then this battery is removed and another capacitor, this was suppose C1, and another capacitor is connected to it in parallel. Okay, that is mentioned in the question. I think it was parallel, if I remember correctly. And now as the battery is removed and the entire system is isolated, so directly we can say that our initial charge should be equal to our final charge. That is our charge conservation. And if the battery is still connected, then we have to keep in that the potential difference is equal to will be constant. V will be always there. Okay, no doubt there will be some, you can say, energy loss, and that will be compensated by the work done by the battery. Okay, so whenever the battery is connected, please make sure that you compensate for the work done by the battery also. Okay, like in this question as well as in previous question, we considered that when the battery is connected, the work has to be done by the battery also. So we have to keep that in mind. Okay, so that because as the capacitance is going to change, the value of their respective is also going to change. So we have to keep that in mind. So especially in case of the capacitors, these are the only two variations which are always there. And sometimes we, like in the, I think, third question, we dealt with that there is a slab which is being inserted, and that is our conducting slab. Okay, and especially in case of our finding of our energy, we have to remember that energy is basically with respect to electric field. Energy will be only present when the value of electric field is not equal to 0. Okay, so we have to keep this in mind. Based on this, we can easily find out our value of our energy. So this completes all the 5 questions. Thank you.